So today we're going to be looking at some examples of greedy algorithms. The first one we're going to be looking at is the coin changing problem. So you have some currency denomination, and a standard one is one with a penny, nickel, dime, quarter, and 100 cents. And we're supposed to devise a method to pay the customer back using the fewest coins. And the intuitive way is to just add the largest value coin that does not exceed what needs to be paid back at each time. So, for example, here we have 34 cents. So we add a quarter, and then we have 9 cents remaining. So we add a nickel, and then we have 4 cents remaining. So we add a cent, and a cent, and a cent, and a cent. With $2.89, we add $1 and $1, and then we have 89 cents left. So we add a quarter, and then we can add 2 more quarters, and then we will have let's see, 75, so that's 14 cents remaining. So we add a dime and then 4 nickels. No, 4 pennies, sorry, not nickels. No, so the first thing we do is we sort the coin denominations, and then we just iterate until we have reached 0 in value that needs to be returned. We select the largest coin denomination, which is less than or equal to x, and then we subtract that and add the coin to our set. Finally, we return. So is this optimal? Does this always give us the best solution? So let's look at some properties here. The number of pennies is always going to be less than or equal to 4. Because if you have 5 pennies, you could replace it with 1 nickel. And then you have reduced your set by 4. We have also the number of nickels being less than or equal to 1, the number of quarters less than or equal to 3, and the number of nickels plus number of dimes is less than or equal to 2. So what we can do is we can replace 3 dimes and 0 nickels with 1 quarter and 1 nickel. And then our set is reduced in size by 1. We can replace 2 dimes and 1 nickel with a quarter, and then we have reduced our set size by 2. So we have a theorem that the cashier's algorithm is optimal for US coins. And if we consider how it would change the value x, which is between these 2 coins. So So coin number k and coin number k plus 1. Now we would claim with this algorithm that any optimal solution must take coin k. And if it doesn't take coin k, it would need coins which are less than coin k to add up to x, but with a smaller set size. And we have this table below which indicates that there's no optimal solution which can do this. So when we remove coin k, we have reduced our problem into a coin changing problem for x minus the kth coin cents. And by induction, that is solved by our cashier's algorithm. So this is just a table for based on the properties we showed before. And you can see that since you can replace 2 dimes and a nickel with a quarter, 24 is the max value you can obtain while reducing your set size as you can. So that is if you don't use any quarter. But is the cashier's algorithm optimal for any set of denominations? And the answer to that is no. So let's look at US postage. We have these really strange values. So we have 1, 10, 21, 34, and then some more. Yeah, 70, 100. That's all we need. And we're gonna apply the cashier's algorithm to 140 cents. So first we would take 100, and then we have 40 remaining. So we take 34, and we have 6 remaining, and we take 1 6 times. But the optimal solution would be to take 70 twice. Another case that can happen is we might not even get an answer. So if we have coins 7, 8, 9, and we want to find a solution for 15 cents, then we would, with the cashier's algorithm, we would select 9 first, and then have 6 remaining. But we don't have a coin that is less than or equal to 6, so we can't do anything. And in this case, the optimal solution is to take 7 and 8. Now there are some properties for this problem which allow you to check if the cashier's algorithm will work, but I do not recall them off the top of my head, and I believe they're a bit complicated. It has to do with the difference between each coin size. Okay, let's move on to interval scheduling. So we have some jobs, and each of them has a start and a finish time. And we say that 2 jobs are compatible if they don't overlap at all. So what we want to do here is we want to find the maximum subset of mutually compatible jobs. So let's think greedily. We'll consider the jobs in some natural order. And if we can take a job, we will. So if the next job we're looking at is compatible with what we have so far, then we just take it greedily. And that's what it means for an algorithm to be greedy. It makes this decision without considering the future at all. So we have a few different ways of sorting. We could sort by the earliest start time. We could sort by earliest finish time. Shortest interval, difference between finish and start. And then fewest conflicts, which so we would count for each job the number of jobs it intersects or overlaps with, and then we would select the one with the fewest overlaps. So starting with start time, if we have some job that starts first but takes a really long time, then we can miss out on these jobs here. You can see that it would be optimal to take these 4 instead of just this one. Shortest interval, if you take just based on the shortest interval, then you could have 2 jobs overlapping here, which could be taken together. The counterexample for fewest conflicts is a bit more tricky. So this one will have 3 conflicts. Each of these here will have 4 conflicts. This will also have 4 conflicts. 4. All of these have 4, and this one has 3. This one only has 2. So we would first take this one. Then we would take this one and this one. And now we can't take any more. So we only get 3. However, we could have taken these 4. Okay, so that leaves only one order remaining, sorting by earliest finish time. So as you see, the code is quite simple. You just sort by finish time, then you check for compatibility, and if it is compatible, you add it to the set. So we can implement this as in O of n log n time. It's the sorting which takes O of n log n time. The iterating is just O of n. Adding to a set is going to be constant time or O of log n. So in total, O of n log n. So we'll just keep track of the job that was added last to our set. And if our current job start time is greater than or equal to the last job's finish time, then we can add it to the set. Let's analyze why this is optimal. And we'll be using contradiction here. So let's assume that the greedy algorithm does not produce an optimal result. we'll create, we'll look at the result provided by the greedy algorithm, which is represented by the sequence of i's. And then we'll have j's representing the optimal solution. Now, there's going to be an element, a first element, in which these solutions disagree. So here we have at index r plus 1 in both sets, we have a different item. But since we sort by earliest finish time first, then the job j r plus 1 has to have a later finishing time, or at least an equivalent finishing time. So why wouldn't we just replace job j r plus 1 with I r plus 1? It doesn't hurt the rest of the result, and it just gives us more leeway here to work with. So you see we change it so it's equivalent. And now we could possibly add more to the sequence of j's here, because we have more. We have an earlier finishing time here, so we might have some job that starts right after, but wasn't compatible before. So the solution here is still good. It's still optimal, and contradicts the maximality of R here, because now we have that R plus 1 is the maximum sequence which they agree on. Next we'll look at interval partitioning. So this is what's done for classrooms. Is we have some lectures which have a start time and a finish time, and we want to find the minimum number of classrooms to schedule all these lectures. And of course, none of them can occur at the same time in the same room. So for example, here we have a schedule which uses 4 classrooms, and there are 10 lectures in total. However, we could change the schedule. So note the change here. We move E and H down to the bottom. F and I go up here, and then J moves down here. So now we have just 3 classrooms being used. And the intervals here are open, so note where these E and H meet, we're only using 3 classrooms here. So if E ends at 2 p.m. and something else starts at 2 p.m., we can those are still compatible. Now again, let's think greedily. So consider them in a natural order, and if we must allocate a new classroom, we will. Otherwise, we will just assign it to one of the already created classrooms. So we have earliest start time, earliest finish time, shortest interval, and fewest conflicts. So for earliest finish time, we would need we would need to take this one first, and then this one is not compatible. And then this one is next in order. And we would add it to, yeah, we could add it here to classroom 1. And then this one will create the third classroom. For shortest interval, we would first be looking at this one here. Then this one creates another classroom. Then this one would be assigned to either one, and finally this creates the third classroom. For fewest conflicts, well, here we have one conflict, here we have two here and one here. So we would take these two first, they each have one. Then we create a new classroom for either one of these, and then add the one remaining. So each time this creates 3 classrooms. But yeah, the optimal solution, of course, is to put this lecture with this lecture here, and then this lecture with this lecture. So we only need 2 classrooms. Okay, so let's go with earliest start time first. So first we sort them, and then we have to keep track of the number of allocated classrooms. And then we want to iterate through all the lectures, and we have to be able to check if our current lecture is compatible with some classroom, just any. And if it is, we just schedule it anywhere. Otherwise, if there's no room, we create a new classroom, number d+1. We schedule the lecture in that classroom, and then we increase d by 1. So this algorithm can be implemented in O of n log n time. We store classrooms in a priority queue, and the key in the priority queue is when the lecture finishes. So what we do to determine if it's compatible with our current lecture is we just compare the value of the start time with the minimum key in the priority queue. So that is the classroom which has its final lecture ending the earliest. When we add the lecture to that classroom K, we have to remove the old key, which we compared with, and add a new one with the finish time of our current job. So the total number of operations done by a priority queue is O of n, and each operation will take O of log n time. The sorting also takes O of n log n time, so in total this is O of n log n. And note that this implementation chooses a classroom whose finish time of the last lecture is the earliest. So let's look at an optimal, a lower bound on an optimal solution. So we call the depth of a set the maximum number of intervals that it can contain at any given time. And we will always need at least that many classrooms, because so for example, if we look at here where the red line is, there's no way to get around needing a different classroom for lecture A, B, and C. So you will need at least 3 classrooms, because the depth here is 3. And if you do take the maximum of this over the entire set of lectures, then that is the depth of the set. And our algorithm earliest start time first will find a schedule which equals the depth. So we know that the classrooms needed are at least depth, and our algorithm finds a solution which has the number of classrooms needed exactly equal to depth. First thing to notice is we will never schedule 2 incompatible lectures in the same classroom. And then let's try to see if we can prove that it is optimal. So let D equal the number of classrooms that the algorithm allocates. We opened classroom D only because we needed to schedule a lecture. That's denoted by J. And that lecture is incompatible with all other D-1 classrooms. So we only do it out of necessity. And these D lectures each end after the start time of our current lecture. Now, since we sorted by start time, all these incompatibilities are caused by lectures that start no later than our current job. So that means we must have D lectures overlapping at time Sj, but it could extend plus some epsilon. Remember that the intervals are open, so if they ended at Sj, then this would be fine. So they extend a bit past Sj. So that means that every single schedule must use at least D classrooms. And therefore our algorithm provides the minimum number. Next up, we'll be looking at scheduling to minimize the lateness. So here we have single resource processes. We can do one job at a time. And each job has some time tj, which is the number of units of processing time it requires, and then it is due at some time dj. If we start job j at time sj, it'll finish at time sj plus tj. The lateness is the max value of finishing time minus due time. So if our job is due at unit 4 and we finish at unit 6, then its lateness is 2. The lateness of the set is the max of all jobs' lateness. So we want to make a schedule for all jobs which minimizes the maximum lateness. And note, if a job finishes before its due time, its lateness is just 0. So again, let's make a greedy argument here. Let's try shortest processing time first. So we'll schedule the jobs in ascending order of processing time. We'll also try scheduling them in ascending order of their deadline. So that's the earliest deadline first. And then we'll try using the slack. So ascending order of slack, which is the difference between its due time and the time it takes to run. So a counterexample to shortest processing time first is we have two jobs. The first job takes 1 unit of time to run and is due at the 100th time unit. The second job takes 10 units to run and it's due at the 10th time unit. Okay, so if we start with job 1 according to ascending order of processing time, then we will delay job 2, which will be 1 time unit too late. So we get an answer of 1 using this schedule. But we could just start with job 2 and then continue with job 1. For smallest slack, we have a counterexample where our first job starts at it takes time 1 to run and is due at time 2. And then we have the same as the last example. We have 10 and 10 for job 2. The slack for job 1 is 2 minus 1, so that's 1. And the slack for job 2 is 10 minus 10, which is 0. So first we'll do job 2.
I think it's the other way around, looking at the equations.
dj minus tj. What do you mean?
You subtract the t from the d, yeah?
Yeah, 2 minus 1.
1 minus 2.
No, it's due time minus time it takes to run.
Looking at the smallest slack scheduled jobs in ascending order of slack, we have d minus t.
Yep.
Looking at the table, you see j in column 1 is 1, dj column 1 is 2.
Yeah, so 2 minus 1.
Yes. Yeah. That would give us 1, and the second one will give us 0.
Yeah. Did I say something else?
I think I understood it in the other way around, but then I would think like the job 1 would be flip the columns. But never mind. I understand the idea.
Yeah. So by processing this job first, we will delay this job by 10 time units, finishing then at time 11, and then our lateness will be 9. However, if we do this job first and then job 2, we will only have a lateness of 1, because now job 2 will finish at time 11. Okay, so we had earliest deadline first as well. Let's look at that. So we sort the jobs in ascending order by deadline, and then we assign the job to an interval. We start at time 0, we just assign it to the current time plus, sorry, the current time up to the current time plus the time it takes the job to run. So we kind of place it down in the time slot which it will be running. We give it start time and finish time. So that's t and then t plus tj. And then we move our current time variable to the end of our new interval. So we set t equal to the finish time of j. Okay, so first of all, there will be an optimal schedule which has no idle time. So if we have idle time, then we're just shifting values to be later for no reason, essentially. So instead of doing that, we just schedule each job right after the next. And that's what we do in our earliest deadline first schedule. It has no idle time. Okay. Now, if we have a schedule S, inversion is a pair of jobs, I and j, such that it says I is less than j on the slides. It means its deadline is less than the deadline of j. So this would be di less than dj. But for some reason, the schedule scheduled j before I. So this I here has an earlier deadline than the j here that was scheduled before it. Okay. So that's gonna increase lateness, having this inversion here. And note that the earliest deadline first schedule has no inversions. So what we do is, with this schedule S, if it has an inversion, and it has to have no idle time, then there's a schedule as well where you swap these two, and if we swap these two, we claim that by reducing the number of these inversions by 1, we will not increase the max lateness. And remember that the deadlines here matter a lot. Deadline I is before deadline J. So if we have L be the lateness before the swap and L prime be it afterwards, and then we have the lateness for each job which isn't these two be equivalent in the schedules. The lateness for I is going to be reduced when we swap. And if job J is late, then its lateness will be its finish time in the change schedule minus its deadline, which was the finish time in the of I in the old schedule minus J's deadline, which is going to be less than or equal to the finish time of I minus I's deadline. And so that's going to be less than the lateness of I in the old schedule. So we're at least, so we're possibly improving our schedule, but it is at least as good. So we can claim that our algorithm is optimal. So let's define S star to be an optimal schedule that has the fewest number of inversions. And we can assume there's no idle time. Now, if there are just no inversions at all, then the schedule we have so far is equivalent to the one produced by the earliest deadline first algorithm. So S is just equal to S star. However, if there is an inversion, then let ij be an adjacent inversion. So these are two adjacent values, but their deadlines are not in order, not in ascending order. So if we just swap I and j, we do not increase the max lateness, and we decrease the number of inversions. So this contradicts the definition of S star. It is not the one with the fewest inversions. Now, these are some greedy analysis strategies, so how you can try to prove that a greedy solution is optimal. And simplest one is greedy algorithm stays ahead. So just show that after each step of the greedy algorithm that its solution is at least as good as any others. So if you can prove that at each step when you make a decision, it must be optimal. Then there is the structural one. So that was like with the depth in the partitioning. So we discover some simple structural bound which assert that every possible solution must have this certain value. and then you show that you achieve this bound with your algorithm. Then there's the exchange argument, or also known as a swap argument, where you just transform any solution to the one found by the greedy algorithm, and each time you make a swap, you do not hurt the quality of the solution. You only make it possibly better. Some notable greedy algorithms are Gale-Shapley, which is stable marriage problem, if I remember correctly. We have Kruskal and Prim, which solve minimum spanning tree. Dijkstra, the shortest path problem. Then we have Huffman coding, and many, many more. Finally, we have optimal caching. So we have a cache with the capacity width to store k items. And we have some sequence of requests for items. A cache hit is when our cache contains the item when it is requested, and a cache miss is the item is not in the cache when it's requested. And when the cache miss happens, we have to bring the missing item, the requested item, into the cache and evict some other item if the cache is full. So we want to minimize the total number of evictions. So an example, we have k equals 2 and the initial cache is AB. Our requests are A, B, C, B, C, A, A. Okay, and the claim here is that the optimal eviction schedule is 2 evictions. So here we requested C, but it was not in the cache, so we had to evict A or B. We evicted A. And then we request B, it's in the cache, C is in the cache, and then we request A. And then we evict C for that, place A in the cache. Yeah. And finally we have a request for B, which is still in the cache. Okay, so what kind of greedy algorithms can we use here? We could use last in, first out, or first in, first out. So we either evict the element which was brought in most or least recently. We also have least recently used. So let's see. Is there an example of it here? Eject D. This doesn't look correct. Eject D. But it's placing D into the cache. Anyway, essentially it is the one which hasn't been used for the longest time. So its most recent access is earliest in history. We also have something called least frequently used. And then we keep count how many times an item has been requested, and we throw away the one which has been requested the least number of times. So what we have as well is something called farthest in future, and this is kind of an algorithm where you know everything. So it's offline. You can process the entire input, and then you can do what you need to do, knowing what will happen in the future. So what we do here is we evict the item which is not requested until farthest in the future. So it's the one we can wait with the most. And farthest in the future is an optimal eviction schedule. So we'll call it a reduced schedule, where we only insert an item into the cache when it is requested. So if you look here, we're inserting B into the cache at this step, but D was requested. But B isn't requested until at this step, so we might as well just wait with it until B is requested, right here. So that'll be a reduced schedule. And given any unreduced schedule, we can transform it into a reduced schedule without increasing the number of evictions. So suppose we bring in item D at time t without a request, and then let C be the item that S evicts when D is brought into the cache. We have the case where D is evicted at time t prime before D is requested again. So like here, we have C, D was not requested here, but we still brought it into the cache, and then it remains in the cache until it is replaced by E, and it was not requested before this time. So here we could have just had C. And case 2, D is requested at time t prime before D is evicted. And again, we might as well just leave C in the cache until D is requested. So here we have one extra eviction in the unreduced schedule, and here we have the same number of evictions. Yeah, now I wanna look at some problems on Lattice. So let's look at minimum scalar. there are a few more slides. It's just a proof. It's very verbose. I'd just be reading off the slides for you. So I rather want to look at some problems first, and then we'll see if we have time for that. Okay, so here we are given two vectors, and we want to calculate the scalar product of these vectors. So that's just the first item times the first item, plus the second item times the second item of the other one, and so on, up to the nth item. Now, we are allowed to permute the coordinates of each vector as we wish, and we want to permute them in such a way that the scalar product is the smallest possible. So if we look at the samples, we get 1, 3, and -5. And -2, 4, and 1. And the sample claims the output is -25. So let's see. If we do -5, 1, 3, and 4, 1, -2, then we get, so let me write this down, 1, -5, 1, 3, and 4, 1, -2, then this is gonna be -20. We'll have +1 and -6, which is 25. For the other case, we have 1, 2, 3, 4, 5. Okay. And then we have just 1, 0, 1, 0, 1. And the result is 6. Okay, so the only way I see getting 6 here with this is 1 plus 2 plus 3. So then it would be 1, 1, 1, 0, 0. Okay. So then we might have an idea. This is in ascending order. This is in descending order. This is in ascending order, and this is also in descending order. So can we greedily sort this, the first one in ascending order and the second in descending order, and then just multiply each value? Is that always going to be optimal?
I think so.
So let's consider what happens. So in this case, we have a negative number. We have the largest. What?
Sorry, you can consider neutralizing the largest number.
Neutralizing the largest number.
You take the largest number, in that case 4.
Yep.
And you minimize it. You just you neutralize it, so to say, by multiplying with the smallest number possible.
Yeah. So that would be -5.
So therefore, at each step, you take the optimal step.
Yeah. So kind of a thing to notice here is if this is a negative number here, which we're multiplying with the largest number, then we will get the largest negative result we can. If it is positive, then we get the minimum positive result we can. Okay, so this should be simple enough to code up. So it's called minimum scalar. Okay, and we get up to 10 test cases per input. So we'll have to read that in. Okay, so per test case we get one integer n. Next we get n integers for the vector x, and then n integers for the vector, no, sorry, the vector v1 and the vector v2. So let's define the vectors. How large can the numbers be? 100,000. Okay, so that's 100,000 times 100,000 at most. So we'll need long here. So we'll have v1 and v2. These are each of size n. And then v1 and v2. Okay, so now we have our values. We want to sort, so we set ascending order for the first one. So let's just sort v1.begin, v1.end. For the second one, we want descending order. I think the easiest way to do that is sorting in ascending order and then reversing. So we sort and then we reverse. Okay, and then we just need to calculate the value of this. So this is gonna be v1i times v2i. And then we have to write case t plus 1 like so, and a new line, of course. So let's try running this. get the correct value and sample, and we've convinced ourselves that the greedy approach is correct. So let's submit. And it is accepted. Okay, another problem I want to look at is Hyman EC. Yeah. It has quite a long statement though. So take some time to read it. I'll post the link in the chat. Oh wait, that's the wrong chat. Sorry. Okay. So we have up to 10,000 problems. The contest time can be up to 10 to the power of 9. And then we get 4 integers A, B, C, and T0. T0 is the time it takes to solve the first problem, and the rest are generated based on the values of A, B, and C. So it's like a pseudo random number generator with a linear congruence. Um, So let's see what kind of a greedy approach can we do here. We want to we want to maximize the number of problems a pikeman can solve within the time limit. And then we have to output the total penalty he will get. And the penalty can be quite large. So we should print it modulo 10 to the power of 9 plus 7. Okay, so how do we do this? What problems do we want to solve first? The only value we have for them is how long it takes to solve them.
So start by sorting it in ascending order of time.
Yeah, in ascending order.
Problems first, right?
And why is that correct? Because if we choose to solve a problem which takes longer than some other problem, then why didn't we just do the one that takes shorter time? It'll reduce our penalty in total, both because it takes shorter time to solve it, so we get less penalty for that problem on its own, and also we will start doing the next problem sooner, so their penalties will be reduced as well. Okay, so let's write code for this. Okay, so first we need to read the input. We have n, we have t. We have a, b, c, and t0. So a, b, c, and t0. And we want to calculate time for each problem. So let's start by creating a vector, placing the first problem as the first element. Okay, and then we just want to create enough numbers for n problems. So while the size of times is less than n, we want to add the next value here. So we'll push back yeah, maybe this needs to be long. Because during the intermediate calculations, the value can get quite large. We have let's see, c can be 10 to the power of 6. So when we take modulo c, it'll be 10 to the power of 6 or less. And a can also be 10 to the power of 6. So at most we get 10 to the power of 12 here, plus whatever b is. So let's use longs for that then. Okay, and the formula they give us is a times the last value, so t dot back plus b modulo c plus 1. Okay, so now we have the time it takes to solve each problem, and we sort it in ascending order. Okay, now we need to count the number of problems we solve. We need to count the penalty as well. And note the penalty is what gets, or the time at which you solve the problem is what gets added to the penalty. So we need to keep track of the current time as well. So we'll need the count. We'll need penalty. And the current time. Okay, so now we just want to try to solve the problems in the order we've given. So let's just start at problem 0. And go all the way up to n. Okay, and if we exceed the contest time, then we're done. So if current time plus the time it takes to solve the problem we're at, if that exceeds contest time, then break. Otherwise, we did solve this problem, so we can increase the count by 1. We also have to increase the time by the time it takes to solve the problem, and then after having solved the problem, a penalty gets added. Okay. At the end, we have to write out the count and the penalty modulo 1000007. Okay, samples are correct. The compiler thing. You'd think after 100 plus times I'd remember it. Okay, so we got accepted for this. Now it's not part of the problem set, but there's a more difficult version of the problem, which if you're interested, you can look at. So what changes here is n grows larger, t grows larger, and that's it. Yeah. So as you might have noticed, the greedy algorithms are often quite intuitive. Like it's something that you can, just try and see if it works, and then maybe you'll get a feel for whether it's, true or not. But it's not uncommon in problems that there is a greedy algorithm which seems optimal but isn't. So you'll get the idea that you can apply a greedy algorithm, but it doesn't work. There are some edge cases. Some things you have to keep in mind when making a decision in the future. Yeah, so the problem set this time around, we have 5 problems and 2 bonus problems. So we have introspective caching and red-blue spanning tree. Those are the bonus problems. The rest are the standard ones. They each give 1 point, and you need 3 points to get a full marks. And these are all problems where you should be greedy. So I'm kind of giving you a big hint here for these problems. You should be greedy. You just have to figure out how. What are you greeding for? Yeah, so the rest of these slides are just proof of an invariant here for the reduced schedule. It is not necessary that you understand the proof, but it can be quite useful. You should be able to solve the problems without completely understanding the proof. Essentially, it's an induction on J. So where we have our farthest in the future schedule, and we have some other schedule which is optimal and reduced, and they agree up to the first J requests. So we consider the cases that can occur for the J plus first request. And since they have agreed up until now, their cache up to this request is their equivalent. And we are requesting item D. If it's already in the cache, then this S prime that we are constructing, which will satisfy the invariant from S, it will just satisfy it directly. We don't need to change anything. However, if D is not in the cache and the two schedules they evict the same element, then it also satisfies the invariant. Then we have the more complicated case. D is not in the cache. Farthest in the future evicts the value E, and the other schedule evicts some other element, so F, which is not equal to E. So we construct S prime from S by evicting E instead of F. And now S prime agrees with our farthest in the future schedule on the first J plus 1 requests. And we show that having the element f in the cache is no worse than having element e. So again, it's this argument that we're not making things worse. Okay, so let s prime behave the same way as s until s prime is forced to take a different action. That happens because either s has to evict e, or because e or f is requested. So let j prime be the first time after time j plus 1 that s prime must make this different action from s. And let's say that g is the item requested at time j prime. So if g is equal to e, this cannot happen with farthest in the future, because there must be a request for f before e. Another case is if g is equal to f. F can't be in the cache of s. So let's say e prime is the element that s evicts. Now if e prime is equivalent to e, then s prime accesses f from the cache, and now s and s prime have the same cache. If e prime is not equal to e, we make s prime evict e prime, and we bring e into the cache. And now s and s prime have the same cache. And then we let s prime behave like s for the remaining requests. Note that s prime is no longer reduced, but it can be transformed into a reduced schedule that agrees with our farthest in the future schedule through step j plus 1. Finally, we have the case where g is neither e nor f. S evicts e, and we make s prime evict f. Now s and s prime have the same cache, and again we let s prime behave the same as s for the remaining requests. So that covers all the cases. And I recommend you read through it. It's quite a long case analysis proof. It can take a couple of read-throughs to fully grasp everything. But let's talk a bit about online versus offline. So most of the problems you'll do are offline. And that's when you get the entire input just in one go. So you'll know the entire sequence of requests beforehand. However, usually in reality, you can't know everything in advance. You usually get some query, and you just have to handle it instantly, just as it comes, and you have to handle it before the next query. So you don't know all the requests beforehand. And caching, as you may have learned in computer architecture, it's one of the most fundamental online problems in computer science. Now, the farthest in the future algorithm is optimal in the offline case, and it can provide some understanding for online algorithms. Yeah, I think that's everything. So are there any questions?
online would use LRU.
LRU?
Yeah, would that?
Yeah. So this here, this K competitive thing here, this is a value that's used to say how it performs versus offline algorithms.
Okay.
So this competitive thing here, it's just a description of how good it is compared to the offline algorithm, if you knew it beforehand.
I didn't.
Yeah, it's
yeah.
not something you see often. There are, so like the problem I showed you when James asked about what square root decomposition can do that segmentary can't. This here, you see it says online here. So this here is an example of a competitive programming problem where everything is online. So you have to process this request, answer it, and then based on the answer you get there, you can process this request. And this is usually done with some XOR or something similar. So if you see something like this in the input where you have to XOR the last answer you had, then okay, I need an online algorithm. I can't do it without doing it online.